was freezing.
Absolutely freezing.
It's freezing this morning.
Yeah.
This morning,
I didn't want to wake up.
Why are you outside?
And if you're wondering what the sick Afrobeat music is,
I don't know if he was college stuff.
I'm sure you guys are wondering. Fella Cootie?
I know Kid Cootie. I know Kid Cootie.
Nobody? I don't know. Somebody in Nocello's class let this know. Fella Cootie, Zombo, tasty Afrobeat. I was like, he does have some tasty Afrobeat. And I found this one, very appropriate song. Teacher don't teach it.
What's listen to Afro? Yeah.
Aphrodisiac?
Because they will blood vessels break.
Okay, so today we are going to do this problem from the problem set. At least I think we're going to do it. Let's do it if you're ready.
The videos were like hard to like follow.
Videos are hard to follow.
Cause like we couldn't see what you're writing on the board.
So I was like, I don't know what he's
It was HD quality.
No, it wasn't.
I don't know.
It was
1080.
very small.
Can you like rent out like one of those?
Can we go over the second part of the
If
video?
you're watching it on your phone, it's very hard to see what's writing on the board.
I was on the computer.
I was on the computer too. You couldn't really see anything.
I just looked.
Like the first part was like stuff
Did
we
you
did
watch it?
before.
Did you change the settings so it was 1080 or 720? If you change the resolution, you'll be able to see it.
Well, if you can't see like what you're writing,
Try again. Try to change the resolution on the bottom right. I mean, all the videos I've uploaded before, you can pretty much read. Well, let me know. Maybe I wrote too small.
Can
Whatever.
we go over like the new, like it was like with energy or something, or like voltage. And, like,
Voltage. Yes, we'll
Yeah,
do that
that's
for
it.
this problem. So it's not part of what's on here, but I'll explain how voltage is related to stuff.
If there's a question about one of the other questions on there, for the second or the third reaction, well, depending on how you look at it, where you have balance upon the redox equation using the table of half reactions below, one of them, I can't find a reaction that works. It's for the SO3 T minus plus, I don't know, 4 minus becomes SO4 T minus and then T plus. I can't find something that gives you SO3 T minus on one side and SO4 T minus on the other.
There's one that's close though.
There's one that has like an H, but it doesn't give you with an SO3.
H2SO3.
Right, but it doesn't give you with the charge.
Well, if it's H2SO3, hydrogen's a +1, SO3's got
So
to be
just break up the ion for it.
Yeah, use that. Okay, potassium dichromate is used to titrate a sample containing an unknown percentage of iron. This is how we do titration. We add something that we know the concentration of to something we don't know the concentration of, and by doing some stoichiometry, we can figure out how much is there. The sample is dissolved in an H3PO4 H2SO4 mixture to reduce all of the iron to Fe2+. Okay, so there's iron in the sample in a bunch of different forms. We want it all to be the same form so it undergoes the same reaction. So that's what this first part is. We need to understand all the iron is iron plus 2. The solution is then titrated with 0.01625 molar K2Cr2O7, producing Fe3+ and Cr3+ ions in acidic solution. Titration requires 32.26 milliliters of K2Cr2O7 for 1.2765 grams of the sample.
A lot of numbers.
Okay, so the first thing you have to understand is what equation this actually has. It says balance the net ionic equation. Using the table 17.1, which is the table I gave you up above, of half reactions. And I can say the key is to find half reactions that contain the species being oxidized and its product, and the species being reduced and its product. One of the reactions will need to be reversed since all the reactions in the table are reductions. So we have potassium dichromate. We're mixing it with iron plus 2. Fe2+. Okay, what does it produce? producing? Fe3 plus and Cr3 plus. Okay, so my guess is we're going to have some reaction that converts Fe2 plus to Fe3 plus, right? And then we're going to have to find one that has this Cr2O7 and Cr3 plus in it. So let's look at it. That you're probably not going to see on the video unless I zoom in. Anybody see it? Okay, I see one in the middle. It doesn't have K2Cr2O7, but it has Cr2O7. Right? Now we don't have to know the solubility rules, but potassium is going to be a soluble substance. Okay, so if you absolutely cannot find K2Cr2O7, try to find something that at least has some of that in it. Okay, so the other example from the homework, if you can't find SO3, you've got something that also has SO3, that might help. Okay, so this is the half reaction for the dichromate turning into the chromium 3 plus. And if you look at some other videos about balancing redox reactions, they're going to be nasty. Because they're going to explain where this hydrogen comes from, where this H2O comes from. We don't need to know that. All we have to know is if we can find this on a table of half reactions, and I get two half reactions that are involved, how do I combine them to get the overall reaction? Okay, so it's quite a bit simpler than what you used to have to do. All right? Now, just because I said I would talk about it, this reaction has a cell potential of 1.33 volts. What does that mean? What's a volt, physics people?
Joule something.
Joule seconds.
A joule per coulomb. What's a joule?
Form of energy.
It's a measure of energy, and what's a coulomb?
Charge.
It's a measure of charge. It's actually an amount of particles, charged particles. Okay, in this case we're talking about electrons. So what this really is telling us is that these electrons that are involved in this reaction, they are gaining energy. They are gaining 1.33 joules of energy per coulomb of electrons. Okay? Now, there's a problem in chemistry in that physicists measure in coulombs, chemists measure in moles. Okay? So on your equation sheet, there's a conversion that allows us to convert between coulombs and moles. We're going to need to know how to do that. We're going to talk about that in the next unit, in 3C. We're going to do actual calculations with these in 3C, so we'll see this again. Okay? But this is basically telling us that as this reaction occurs, electrons are gaining energy. Okay? If it was negative, that means they're losing energy. Right?
Yeah.
Okay. So, we need to find the Fe reaction. Fifth from the bottom. The eagle eye. Okay. Now this says Fe3 plus turns into Fe2 plus. But we have 2 plus turning into 3 plus, right? That's okay, we just flip it around. So Fe2 plus turns into Fe3 plus by giving off an electron. Now, they might ask us which one of these is the oxidation and which one is the reduction. Well, since this is a table of standard reduction reactions, the one that we wrote as it was written has to be the reduction. But let's assign oxidation numbers to see who's actually being reduced. All right, Cr2O7. What rule in our oxidation number rules are we going to run into first?
-2 for oxygen.
Oxygen. It's not a peroxide, so we're going to call oxygen a -2. If there's 7 of them, that's -14, but we really want to be -2 anyway, right? So that means
Plus 6.
Each of the chromiums has to be a plus 6.
Oh.
2 chromiums at plus 6 will give us plus 12, and then the minus 14 will give us an overall of minus 2. Hydrogen here, same as its charge. Chromium over here, same as its charge. Oxygen here is the minus 2 rule, and hydrogen is the plus 1. So who's undergoing reduction?
Chromium.
Chromium. It's going from a plus 6 to a plus 3. How do you go from a plus 6 to a plus 3? You have to gain electrons, right? To become less positively charged, you have to gain negative charges. So it's gaining 3 electrons when it goes from a plus 3 to a plus 6. Gaining electrons?
Reduction.
Grrr, that's reduction.
Wait, can you explain that? I'm confused about that.
Losing electrons.
Losing
Oxygen.
electrons.
If you gain electrons, you're undergoing reduction.
Okay.
If you lose electrons, you're undergoing
Oxidation.
That makes so much sense.
I know, you've been looking at that thing all year going,
I've
what?
been looking at it since sophomore year.
Since sophomore year, man. Tension.
I never understood.
Okay. Here we got a plus 2 to a plus 3. How do you become more positively charged?
Lose it.
You lose your electrons. So this is the oxidation. This is the reduction. Redox. Right? Now the key thing in writing our balanced redox reactions is what? The absolute thing you must do. Balance the electrons. Okay, we've got 6 electrons being gained here. We've only got 1 electron being lost. That's a problem.
Yep.
We need the same number of electrons being gained as we have electrons being lost. So what we're going to have to do is we're going to have to multiply this whole reaction by 6. So it's actually pretty easy. Once you know what the 2 half reactions are, absolutely have to make sure that the electrons are the same in both half reactions. Okay, you also have to remember if it's a table of reductions, you're going to have to reverse one of them. Okay, but that should be obvious if they describe what the reactants and products are. Okay, so for this one it's pretty simple. I'm not going to like multiply this all out by 6 and then add it. I'm just going to do it all in one step. So we're going to have Cr2O7 2 minus plus 14 H pluses plus 6 electrons plus 6 Fe2 plus. Just add up everything on the left side of both half reactions. Then we'll do the right side. 2Cr3 plus 7H2O plus 6 Fe3 plus 6 electrons. Just like we did with going from a full ionic equation to a net ionic equation, if something's present on both sides of the reaction in the same form, we can cancel some out. Steve?
How'd you get that big reaction?
Which one?
Like, yeah,
This?
how'd you write?
I'm just adding up everything on the left side of these 2 reactions. Over here, I'm adding up everything on the right side. I multiplied by 6 here before I added it together. I did that in my head. All right. So because we have 6 electrons on the left side and 6 electrons on the right side, we can just cross them out. If you have any electrons left in your overall reaction, you did it wrong. Okay? They must cancel. Now in this reaction, there's nothing else that cancels out. That's not always going to be the case. You can see how many of these half reactions have H plus in them. A lot of times you'll have some H pluses on both sides. Now they might not all cancel out. If I had 14 H pluses here and 10 H pluses here, I can only cancel 10 of them on each side, and so I still have 4 on the left side. Okay? A lot of times water, H2O, will be present on both sides. So you can cancel some of them, but not all of them. Electrons, though, you're going to cancel all of them. Okay? So this is the overall balanced equation, which gives us the stoichiometry between the dichromate and the ion. Without writing this reaction, we wouldn't know how many moles of dichromate it takes to oxidize our iron. Okay, so that's the purpose of writing that balance equation. All right, what's next? Determine the percent iron in the sample. Okay, well, we've got this massive sample. It's 1.2765 grams. So we can probably say that the percent Fe is mass of Fe over 1.2765. Right? That's how we find a percent mass. But we need to know the mass of iron. Do they tell us the mass of iron? No, they tell us that titration requires 32.26 milliliters of potassium dichromate. And they told us the concentration of the potassium dichromate. So what we're going to have to do is we're going to have to do some solution stoichiometry.
Wait, so the H3PO4 and H2SO4 is like, we don't care about those?
No, all they did was to get any iron in the sample, turn it into iron 2+. The last question on the problem set, you've actually got a mixture of two different forms of iron. So in that case, you actually have to do 2 titrations to figure out each of the ones separately, and then you can combine them to figure out the total iron. But in here, we did a little trick. We said, let's just add some acid. That's going to make sure everything's iron +2 to start with, and then we can just figure out the total iron in one titration. Okay. We're going to use a definition of molarity, which is
Moles over liters.
mole solute over liters solution, which some of you are going to need to review, judging by the results of the last quiz, which I will pass back tomorrow. So, the molarity of the dichromate solution is 0.01625 molar. It said it took 32.26 milliliters, which is 0.03226 liters. So let's solve for x. What is it? 5.242 times 10 to the negative 4? What are the units?
Moles.
Moles of what?
CR07, CR2, chromium.
Those are moles of potassium dichromate. What is the ratio between the moles of potassium dichromate and the moles of dichromate ions? 1 to 1, right? There's only one CR207 in this. So we can say what we really had was 5.242 times 10 to the minus 4th moles of CR2O72 minus. Right? That's an important step only if there's more than one of the ion we're interested in, right? If this was, I don't know, vanadium 4 dichromate, then whatever the concentration of vanadium dichromate we found would actually be twice as much dichromate in there. Okay? But because here we only have one dichromate ion in this molecule, the number of moles of dichromate is equal. Okay? Now what? Now it's stoich time. Balance equation tells us for every 1 mole of CR2O72 minus, we're going to be able to oxidize 6 moles of Fe2+. So what do we get?
Why don't you stick the, if you're trying to find grams, why don't you just stick the grams?
Oh, I could. Sure. If I know I'm going to grams anyway, I can just go, well, actually there's 2 steps I really should do there. Hold on 1 second though, I need more sig figs.
3145.
3145? Now technically that's moles of Fe2 plus, right? What we wanted was the mass of Fe. How are we going to do that?
And then convert to grams. So 1 mole of Fe is equivalent to 55.85.
Just say that again louder.
So that's 55.85 grams of
There's a step you're missing.
iron in 1 mole.
1 mole of Fe2 plus came from 1 mole of iron.
Oh.
Okay, technically, if we're really trying to find the amount of neutral iron that was in there, there's a little step we should do. Okay, then I can use the molar mass of iron. 55.847. And what do we get?
0.176
0.176.
grams. 0.1756.
0.1756, 0.1756 grams of Fe in this sample. Okay, so once we know that, we can figure out percent iron in the sample. Wow.
So, how many? Do you need 5 sig figs for your percent as well?
Well, we have 4 sig figs in our titration volume. We have 4 sig figs in our molarity. We actually have 5 sig figs in the overall mass, but this we're really only going to know to 4 sig figs, right? So you can keep all the digits here before you divide, but your answer should be 4 sig figs. What do we get?
So 13.76.
Okay? In these problems, again, step 1 is to look at the half reactions, find the 2 that you need, reverse one of them, make sure they have the same number of electrons, add them together, and do some canceling. That's going to give you the stoichiometric ratios. After that, they're going to give you some amount of one thing, and you're going to have to stoich it to an amount of something else. It's going to be either solution stoichiometry, or maybe gas stoichiometry if some of these are involving O2 gas or something like that. They can throw gas stoichiometry at you, right? But it's basically just stoichiometry using this big, nasty balance equation. They will give you the table of half reactions, for sure. It says specifically in the outline that students can balance the half reactions, or sorry, balance. Just read it. Stop trying to think I know what it says. Who's got a hand? Yeah, fine. Should be 3B3.
Students able to identify redox reactions and justify identification.
No, part C. Balanced chemical equations for redox reactions can be constructed from tabulated half reactions. So they're going to give you a table of half reactions, and you should be able to figure out the balance equation for that. Okay? So these are the tabulated half reactions. Okay. Now there's one last step that we're supposed to do in this problem. We're supposed to figure out what substance it actually is. How would we do that? These are all iron plus 2 compounds, right? So we'd have to figure out the percent mass of this, the percent mass of this, the percent mass of that, see which one's 13.76. Whichever one matches, that's your answer. Question?
8 just means that there's an oxygen attached to it. So that's IO, PO.
Iodate. Yeah, they're usually polyatomics with oxygen on them, but yeah, you'd have to know the polyatomic ion.
How do we, like, should we memorize those? Or?
No. They're going to give it to you, So I should have written it on here.
Okay.
I think it's IO3 for iodate, phosphates PO4, acetates C2H3O2.
And then, what are the charges of those to balance it with?
Oh, iodate is IO3 minus 1, phosphates PO4 minus 3,
So it's FeIO3 in parentheses 2,
yep,
and then phosphate is PO4,
PO4 minus 3,
so Fe3 parentheses PO4 2.
correct. Acetate is C2H3O2
What's the short one?
minus 1.
C
Say it one more time.
C2H3O2.